clearly audible now? Okay, I shall use another terminal.
Sir, hello.
Just wait.
Sir, voice is very low, sir. It is not audible, sir, clearly.
Now okay?
Yes, sir. Yes, sir. Now it is okay, sir.
Okay, okay.
Sir, shall we start, sir?
You can start now.
Okay, sir. Okay, sir. Thank you, sir. So, good morning to all. Uh, uh, so, Dr. Lalit Chandra Saikia sir is with us. So, he is eminent speaker in this session. So, Dr. Lalit Chandra Saikia sir is presently working as associate professor in Department of Electrical Engineering, National Institute of Technology, Silchar, Assam. Uh, Sir having more than 28 years of experience. So out of this, 5 years industrial experience and 23 years of teaching experience. So Sir has started his career in 1992 in Northeastern Drilling and Work Overseas Limited. So he has worked in this industry from December 1992 to December 1993. So from December 1993 to November 1997, Sar has worked in ONGCL, Sipsagar, India, and he has worked as a lecturer from December 1997 to December 1999 in Electrical Engineering Department, Jorhat Engineering College, Assam. And Sar has joined in NIT Silchar in January 2000, and he is now working as associate professor. Sar having total 53 general publications. So out of 53 general publications, 49 are SCI journals and 4 are Scopus journals. And Sar has published 57 conference publications and 16 book chapters. So again, I am welcoming you, sir, for this
Okay.
FDP. Please
Okay,
share your
thank you,
please share
Chiranjeevi,
your
for
slides.
your nice introduction.
Thank you, sir.
Also, I would like to thank all the committee members of this faculty development program for inviting me as a resource person for this program. Today I am going to deliver a lecture on hybrid AC/DC microgrid and its control. This is purely a technical session. The materials of this particular session is taken from some literature review on the microgrid, and from that I have prepared this lecture. Okay. Hope it will help all the researchers in the area of microgrid. Okay, let me present the slide. Is it visible?
Yes, sir. Visible, sir.
Is it visible?
Sir, now not visible, sir. Previously it was visible, sir. Yeah, now it is okay, sir.
Voice is also okay.
Yes, sir. Yes, sir. Okay, sir.
Actually, I
Sir, your voice is very low, sir.
voice is low. Okay.
Yes, sir. Yes, sir.
This wait. Now okay.
Yes, sir. Okay, sir.
Okay. Okay. Uh, so the title of my presentation is Hybrid AC/DC coupled microgrid and its control. Um, so the outline of my presentation is these are the outlines. If I say one by one, it will again take time. Let me go to the next slide, starting from the introduction. Okay. Now, at the introduction, just I introduce what is the need of microgrid and why renewable energy power extension from renewable is required. It is required to penetrate more power from the generating units due to increased demand. This is one of the reasons that we have to cope up with increased demand. It demand increase due to living standard, population growth, population pollution, depletion of conventional energy resources like fossil fuels. It may be coal, petroleum, natural gas, etc. So this making the situation more critical. Critical means we have to penetrate more power from the generating units to the demand. So fossil fuels have their own disadvantages like emission of carbon dioxide, nitrogen gas, sulfur oxide, which cause pollution and global warming. So the major disadvantage of central generating unit plants is their inefficiency because of poor waste heat recovery and line losses in today's power generation. Now, the main theme of FA microgrid is main component is DG, that is called distributed generation, and its technology is called DG technology. So it encompasses a wide range of distributed energy resources. Okay, distributed energy resources means say these DGs refer to a variety of technologies that generate electricity at or near where it will be used. And emerging DG technology with associated local loads and its control units is the microgrid. That means in a microgrid, there are numbers of DG, that is distributed generating source or generation source. So along with its control, say we can microgrid. Okay? So this microgrid can improve efficiency through combined heat and power, increase overall transmission utilization, provide backup power and premium power, employ renewable energy, example PV, wind energy, and it decrease greenhouse gas emissions. So microgrid can do these things. Okay. So one feasible way to realize sustainability and resilience enhancement is to make changes based on the existing infrastructure and apply microgrid. That means to supply the demand, increase demand, so to make the system more reliable, a sustainable one, and to increase the resilience, we have to connect the microgrid along with the existing infrastructure. So an existing infrastructure in case of power system is our normal power system. Okay, if we connect microgrid, then this can be obtained. So now what is the definition of the microgrid? A microgrid is an aggregation of distributed generating units, DG, or you can say distributed energy resources, or distributed energy storage, DES, or sometimes we can say energy storage system, and sensitive and non-sensitive loads. Okay? A centralized or decentralized control system, and operating as a controllable subsystem which can operate in grid connected as well as islanded mode of operation. That means in a microgrid, there are numbers of distributed generating units like say wind energy conversion system, PV power plant, micro turbine, fuel cell, reciprocating engine, so storage devices, battery energy storage system, etc. Along with its control, along with its control, and with this, there are some loads. That loads may be sensitive load or it may be non-sensitive load, uh, non-sensitive load. So it may be connected to existing grid. Say this is central grid, existing grid. It can be connected with the existing grid. We can say grid connected. If you don't connect with the existing grid, we can say this is islanded. Islanded. This portion represents the microgrid, microgrid, and this represents this. If you connect this one, then we can say this microgrid is connected to grid. Okay, so this load may be AC load and DC load, and this AC and DC load may be sensitive and non-sensitive. Now see again that definition of the microgrid. Say what are the components in a microgrid? Mainly, these are essential components. Without consumer, there may not be a microgrid. So that means loads must be there, and micro sources, say PV system, wind energy conversion system, etc. Then along with this, energy storage also included. So this is DSO, that means distributed system operator. So it mainly represents the control of these sources and the energy storage devices along with the customer. And this is supplier. When we connect this one to existing grid, then we can say this is grid connected. So nowadays, we can connect some controllable, and we can do that controllable and shiftable load. That means load management also we can do in a microgrid. Electric vehicle can also be connected in a microgrid, and storage. So whatever the storage in the substation, that also be connected, but these are optional. So from now we came to know that there must be load, there must be micro sources that may be that's generating disease and the energy storage, and there is some control system, and this ultimately connected to grid. It may be when it is connected to grid, we can say grid connected. When you are isolated from this energy supplier, then we can say islanded. So what is not a microgrid? So in the definition, we know that there must be some micro sources, DGs, energy storage devices. So among these, say, if these micro sources are not available, then we cannot say that this is a microgrid. If you say in a system of microgrid, there is no load, then you cannot say this is a microgrid. Okay? If there is no control also, you cannot say microgrid. So another thing is that insufficient carbon credit. If this is also not there in some country, we can say that this is also not microgrid. Insufficient carbon credit means now say so there is some environmental protection that is taken care of the microgrid care by the microgrid. If this protection is not there, then also we cannot say microgrid. But this is optional for countries like us. So in our case, environmental protection, this is not included in the definition of the microgrid. So why this microgrid is required? Proliferation of renewable energy sources, government policies for reduction in the fossil fuels, use of fossil fuels, to improve reliability, sustainability, and efficiency of the modern power system. So increase overall transmission utilization, provide backup power and premium power, decrease greenhouse gas emission. Now come to this classification of microgrid. So there are a large number of means and there are three categories of microgrid. Different author may say define these three categories in different way, but mainly we can say from this reference 19 to 29, we will get three types of microgrid. One is called AC microgrid, other is called DC microgrid, and third one is called hybrid AC-DC microgrid. Okay? So in AC microgrid, come to this AC microgrid. So the DG units and energy storage are connected at some point within the distribution network. So the part of the network consisting of DG units, energy storage system, and local load circuits can form a small isolated AC electric power system. That is AC microgrid. In most cases, the AC microgrid system operations adopt voltage and frequency standard applied in most conventional distribution system. Now see picture of an AC microgrid. This is a picture of a AC microgrid, and this is utility, our existing power system. So at the point of common coupling here, if you want to connect this structure, microgrid structure, to the utility grid, here we have to switch on. So if you disconnect, then this is isolated. Now here see, here two lines, low voltage AC line. This is one line, low voltage LC line. This is also a low voltage LC line. Here two lines are shown, but we can use only one line, one low voltage AC line. This is low voltage AC line. Okay. So all the DGs, that may be some DC DG like PV system, or some AC DG like say wind energy conversion system. Okay. So this wind energy output of this one is AC directly connected to this via converter. So here output is DC, and DC is converted to AC via one power electronic converter to this. So then you will get AC, it is connected to AC bus. That means there is one AC bus. AC bus, all DC DG like PV arrays, AC DGs, along with this energy storage. Energy storage means this energy storage unit is connected to this. So this power electronic interface means energy storage. Output of this energy storage is DC. It is converted to AC using this power electronic converter, and it is connected to AC bus. So AC load can be directly fed from here. We can connect AC load here. Then DC load, to supply the DC load again, we have to convert AC to DC using power electronic converter. Then we can supply this one to DC load. Now, one DG unit, say this is hydro turbine. One hydro turbine, small hydro, etc., also we can connect with this microgrid. This is small hydro type power generation. So that is connected via this transformer, since output is of this one is different, this one is different. We are not using this power electronic converter, one transformer here. So you will get the actual AC, and it is connected to AC line. AC loads are supplied directly from this. If voltage is same, we can connect directly AC load to the AC bus. So this is AC microgrid with mixed type of load. Means DC load is there, AC load is there, mixed type of DGs. Say this DG PV, wind energy conversion system, other energy storage, all are here. So this is AC microgrid. Now come to the DC microgrid. So here part of the network consisting of DG units, energy storage system, and load circuit can form a small isolated DC electric power system. That is an DC microgrid. Okay. So instead of that AC bus, there is a DC bus. This is DC bus, but this is low voltage DC bus, low voltage DC bus. Now our utility is AC. So to get this utility voltage AC voltage, we have to again convert this low voltage DC to utility voltage level using power electronic. So AC loads are connected via this power electronic converter. Since this is DC, we have to convert DC into AC using this converter. This is wind energy conversion system. That means this is one AC DG, AC distributed generation. So this AC should be converted to DC, and should be connected to DC bus. That means main difference between AC microgrid and DC microgrid is that here this bus is DC bus. So we connect all the DGs, that may be AC DG or that may be DC DG, to the DC bus via power electronic converter. Along with this storage unit. Other storage units are also connected here. So here DC loads are supplying, this is fuel, so this is PV area. AC load, if you want to supply AC load, then this. So this is DC microgrid. Now come to this hybrid AC-DC microgrid. Hybrid AC-DC microgrid is a microgrid that contains both AC and DC power sources, AC and DC loads. That means mixture of AC-DC. Mixture of AC-DC. Sources are also AC-DC source, and loads are also AC-DC source. This hybrid AC-DC microgrid considered to be most possible future distribution and transmission system. So now come to the structure of this AC-DC hybrid AC-DC microgrid. So depending on how these sources and loads are connected to the system and how AC and DC buses are configured, the structure of hybrid AC-DC microgrid can be classified into AC coupled microgrid, DC coupled microgrid, AC-DC coupled microgrid. It may be AC coupled hybrid microgrid, DC coupled hybrid microgrid, AC-DC coupled hybrid microgrid. Now see what are they? AC coupled microgrid, all the sources DC, DG, AC, DG, energy storage, all are connected to one AC bus. Okay, and DC load is directly supplied from this AC bus, and if there is some DC load, that can be supplied via one power electronic converter rectifier, AC to DC rectifier. And when grid connected, when we want to connect this one to utility grid, directly AC bus can be connected to this. So this structure is commonly used when dominant generation sources in microgrid produce grid level voltage. This is there is a voltage level here, produce grid level voltage, AC voltage directly, such as from diesel generator. So here there may be diesel generator also there, or indirectly through interfacing power converters. So here this is one power electronics converter. This is one power electronics converter. This is one power electronics converter. This is bidirectional. So this storage element is sometimes it takes power from AC bus that is charged, and sometimes it supply power to this AC bus. So this is bidirectional. So this is AC oblique DC AC. Since this is AC distributed, output is AC. Now AC cannot be directly connected to this, since AC distributed generations are intermittent in nature. So output AC is not fixed. So we have to make it fixed. That is AC bus voltage level. Frequency should also be kept fixed. So again it is converted to DC. Again DCT converted to AC. By controlling this power electronic converter, we can make output of this one is fixed. Similarly, here also by controlling this DC-AC converter, we can make the output fixed. Okay? So DC coupled microgrid. Here, in case of AC coupled microgrid, all the sources, it may be DC DG or it may be AC DG, all are connected to AC bus, but here all are connected to DC bus. All are connected to DC bus. So this is DC. So DC DG is connected to DC bus. AC DC also, DG also connected to DC bus. Storage also connected to DC bus. But this microgrid should be, sometimes it is required to connect with the utility grid. So we have to connect AC. This is AC. We have to connect AC with it. So there must be one AC bus here. So that AC bus, what happened? It gets power from the sources DC DG, AC DG storage element via this DC bus. Now to supply power to AC bus, it is converted again to DC to AC, DC to AC. So it is connected to AC bus. Now this AC bus is connected to utility grid. So this voltage should be fixed. We have to make the AC bus voltage, DC bus voltage fixed at the reference value. So to make it fixed, it is required to control this power electronics converter. So AC load can be directly supplied from here. DC load can be direct supply from this bus also, but there is one converter is required. DC load directly from here. Here DGs and SCs are connected to common DC bus, and this converter, this is called interfacing converter, IFCs. Interfacing converters. So interfacing converter is used to link the AC and DC buses. This structure can be used when DC power sources are major power generation unit in the microgrid. So in AC coupled microgrid, certain AC DC couple means there are two AC and two bus. One is AC bus and other is DC bus. And all these sources, that may be AC DC or that may be DC DC or energy storage, all are connected to each bus. If say DC-DG is here, AC-DG is here, energy storage are here, we can connect this one to DC, or this bus also, we can connect this one to AC bus also. So that means couple, means all the DGs are connected to DC and AC bus. Irrespective of type, it may be AC-DC or it may be DC-DG, we can connect in any bus. Okay? So there is this converter now, it is called interlinking converter. In case of DC microgrid, this is interfacing converter. This is called interlinking converter. Okay? So here in some of the literature, it is like this. This is DC bus, this is AC bus. AC DGs are connected to AC bus, and DC DGs are connected to DC bus. Energy storage in both. Okay? In some literature, it is defined like this. But there is no hard and fast rule. We can connect AC-DG, DC-DG storage element either of these two buses. Okay? So DC loads can be supplied from DC bus, AC load from AC bus. If it is required to supply the AC load from DC bus, there is one converter required. So converters now plays an important role, since here see DC DG, this is mainly say power PV system, AC DG with energy conversion system. This system, whatever the output voltage, output that is fluctuating in nature, intermittent in nature, not fixed. We have to make it the fixed at the reference voltage of DC and AC bus. Now to make it, to control this voltage, it is required that this converter should be controlled. This power electronics converter should be controlled. Now, what are the power electronics converter here? The converters utilized in microgrid operation can be categorized as grid forming, grid feeding, and grid supporting. Now, this grid forming is mainly operated in islanded mode of operation. It is operated as AC voltage source. AC voltage source, we can represent that with a series impedance along with the source. So AC voltage source with low series impedance in islanded mode of microgrid operation, which sets voltage and frequency reference for the microgrid in the absence of main grid. Okay? So grid feeding converter is operated as a current source. This is just like a current source with high parallel impedance, capable of injecting real and reactive power. This P and Q, capable of injecting real and reactive power. So grid feeding converters. So this grid forming converters, which sets the voltage and frequency, this E and frequency means speed, uh, can set, which sets the voltage and frequency. So this is grid forming and this is grid feeding. Now grid supporting converter can operate in both grid connected as well as in islanded mode, includes features of grid feeding and grid forming. So this is our grid forming and this is grid feeding. Okay? This is grid feeding, already we got. So features of these two, both are included here. This is P and Q, this is W and this omega, this speed or frequency you can say. So both features, P and Q features is there. Here P and Q already there, here omega and this also there. So this is, we can use this one as current source based grid supporting converter. And this is voltage source based grid supporting converter. All are here, all parameters are here. So responsibility of these microgrid controllers, the main control variables in the microgrid are voltage, frequency, active power, reactive power, V or E, frequency F or omega, active power P, reactive power Q. These are the control variables. Thus, the microgrid controllers are responsible for voltage and frequency regulation under any operating condition, P and Q control to achieve proper power sharing under grid connected as well as islanded mode of operation. That is, first responsibility is that to control the voltage and frequency, number one, in any operating condition. Number two, P and Q control to achieve proper power sharing under grid connected as well as islanded. A seamless transition from grid connected to islanded mode and vice versa. Sometimes we want to connect the microgrid to the grid, then from islanded mode to grid connected mode. So sometimes we have to disconnect the grid, we shift from grid connected to islanded mode. This is called transition from GC to islanded mode or islanded mode to GC, grid connected mode. So this transition should be seamless. So participation in the energy market with optimized production of micro sources. So responsibility of this one is again to participate in the energy market. Uninterrupted supply to critical loads such as schools, hospitals, and other essential services. So capability of black start in case of grid failure. Optimize operating costs of production and power exchange with the utility grid. So hierarchical control structure of microgrid here. Key control, hierarchical control structure of microgrid comprising of primary control, secondary control, and the tertiary control. So here primary control. What is primary control? The primary control is the control action by the local controller at the grid or load interfacing converter terminal. So grid and load interfacing converter means this is this is load interfacing converter. Load interfacing converter. This is this is grid interfacing converter. Grid interfacing converters. This is like this. So the main objective of this control are fulfilled by accurate P and Q sharing among the user unit by incorporating the power controllers, mainly voltage source converter terminal voltage magnitude, and the frequency by using the voltage controller and achieving required filter inductor current by applying current controller. Hence, this primary control provides internal control of the converter, output voltage and current, as well as power sharing using centralized or decentralized control technique. As the primary control is the fastest among all the levels, it includes islanding detection, power sharing, output control, and subsequent change of controller mode. The controllers for current control can be classified as linear and non-linear. Linear types a PI, PR, proportional, resonant, predictive, deadbed controller. These are proposed by this literature. So these are linear, and some controllers are non-linear, like a fuzzy logic controller, neural network controller, etc. So second one is secondary control. The secondary control is the energy management system of the microgrid. It is responsible for power quality enhancement, restoring frequency and voltage in the microgrid caused due to primary level control action. So this is nothing but the energy management system, the secondary control. It is responsible for power quality enhancement, restoring frequency and voltage in the microgrid caused due to primary level load control action. It is also responsible for resynchronization of microgrid to the utility grid. That is, say we want to connect the microgrid into the utility grid, so resynchronization need to be done. So this secondary control is responsible for it. Secondary control possesses the frequency and voltage error deviation to produce control signal for the error correction, which is sent to the primary controller in islanded mode. Secondary control can be centralized, decentralized, or distributed in nature and of its operation. So tertiary control, this purpose of tertiary control is to manage the power flow between microgrid and the utility grid. This is, it manages power flow from microgrid to utility and utility to microgrid, like that. So tertiary control coordinates the operation of the multiple microgrid and communicates the requirements such as voltage and frequency regulation from the large-scale utility grid. Tertiary control receives power reference from the distribution management system and processes the error between the actual and the reference grid. So what are the control techniques in different microgrids? Now for AC microgrid, these are some of the already proposed techniques. In case of control, primary control level, it may be centralized, it may be conventional group control, it may be improved group control. Nowadays, VP group or FQ boost group control, Q differential voltage, QV group, angle group control, virtual impedance group control, like that. These are under this. Secondary control, distributed approach, multi-agent based technique, model predictive control based consensus, as is missing here, consensus based and centralized approach. So tertiary various control techniques not available till now but limited. Okay. Now here these are some control techniques proposed by different authors. Whether this is practically implemented in microgrid or not, it is not known to me. Okay, these are proposed by different authors in different publications. Similarly, here also. So, similarly, control techniques for DC microgrid, it may be decentralized. Under this decentralized primary control, conventional loop control, virtual resistance based loop control, adaptive loop control, intelligent technique based loop control, mode adaptive loop control, etc. Secondary may be distributed secondary control, centralized secondary control, under distributed control. These are some of the proposed methods, control techniques. Similarly, there are few in the tertiary. So control techniques in hybrid AC DC microgrid, hybrid AC DC microgrid, couple microgrid. Here it may be centralized, it may be decentralized, secondary, centralized, decentralized, distributed. Okay? Under decentralized, these methods are already proposed. So literatures, presently there are many literatures, we may include more here. More here. Now, what are the control strategy? Control strategy and power management scheme for AC coupled microgrid. Now, here see, this is already, we have shown that this is AC coupled microgrid. All the DGs are and energy storage elements are connected to AC bus, to a common AC bus via power electronics converter. And utility grid is connected from this AC bus. AC load directly we can supply from AC bus if voltage setting is same as the load voltage, and AC DC, if DC load is there, that can be supplied from here. Now we this control strategy for and power management scheme for AC coupled microgrid. So as we know, there are two modes. One is grid connected, or another is islanded or standalone mode. Okay. In grid connected mode, these are connected to utility grid. Okay, utility grid has fixed frequency, fixed voltage. Okay, fixed frequency and fixed voltage. In this case, it is grid connected, so this AC bus voltage and frequency is in general maintained by this utility grid. Frequency of this AC bus voltage and magnitude of the voltage of this is maintained by utility grid. Okay, in grid connected mode. In standalone mode, this is not connected. This utility grid is not connected. So we have to maintain the fixed voltage, fixed AC voltage here, and fixed frequency here. So this should be done by maintaining or manipulating by controlling these converters. Okay? How it is done? Say it is grid connected, it can be said as dispatch mode or undispatched mode. In dispatch mode, this microgrid, this may be work as a source or load. Here see this one, dispatch mode. Uh, Power exchange between the microgrid and main grid is dispatch. That is, this microgrid behaves like a controllable source, or it may be act as a load. That means in grid connected mode of operation, it may source, it may supply to the utility grid, or it may collect from this. It may act as a load, collect from the utility grid. So this is called dispatch mode. Okay, so in dispatch mode, main microgrid behave like this and can provide valuable grid support or load management function as a whole. And to realize this, SCR storage elements are inevitable. Okay, so DG and SC operate on power control mode. This DG and AC. DG may be AC DG like wind energy conversion system, or DC DG say PV storage element. All are dispatch power control mode. That is power balancing mode. Okay. So dispatch power control mode. What is dispatch power control mode? It may be power control can be realized by current control or voltage control. In current control, popularly used for grid connected operation, this is output current is control. to track the reference power, and output voltage and the frequency is determined by the grid. Output current is controlled to track the reference power, voltage and frequency are determined by the grid. And in voltage control mode, this is output voltage is controlled to regulate output power. And DG behaves like a synchronous generator. That means in this case, DGs means PV, wind energy system, etc. These are actually power control mode. Power control mode may be current control mode. That is output of the DGs are output current of the DGs are control. Control. Output current of the DGs are control. In case of voltage control mode, output voltage of the DGs are controlled to regulate the output power. Here, in case of current control mode, output current of the DGs are controlled to regulate output power. Okay, so this one is also like this storage element. This storage elements also work like this. Operates in power control mode. So to produce this dispatch microgrid output power, power balancing schemes within the microgrid are used to share dispatch power among the input sources. It can be used in both grid connected and standalone operation. Means voltage control modules can be used as both. So similarly, the other grid connected mode of operation is called undispatched output power. Here DGs, this DG, DC DG, AC DG work on MPPT control, that is maximum power point taking control mode. Maximum power point taking control mode, this DGs. Okay, but AC is typically surging mode. In this case, ACs are taking power from the grid. That means they are surging. Here ACs are dispatched. They are utilized for power control in case of dispatch power. So here this undispatched power, all generated powers are fed to the grid here. DGs work on maximum power point tracking mode and ACs are surging. Moreover, ACs can be controlled to smooth DC's output power oscillations, especially for DGs with intermittent nature, such as wind and PV system. However, both dispatch and undispatched power mode, the microgrid can be used for grid support by controlling active and reactive power delivered to the grid. This grid support will be included in the dispatch reference microgrid power in the dispatch power control mode. In the undispatched power control mode, grid support function will be realized individually through the DG or SC IFC. So the grid support function will be realized individually through DG or SC IFC. DG or these are interfacing converter. These are DG interfacing converter, DG interfacing, this is SC interfacing converter by controlling this. Now come to the standalone operation. In standalone operation, this DG, DC DG, AC DG and SC. AC bus voltage frequency control mode. So in standalone operation, this is disconnected. So this should be maintained fixed. Frequency should be maintained fixed. And demand power sharing. So power sharing, this load should be supplied from here. So this should be supply. Demand power sharing. How this will share how much load. This will share how much load. This will share how much load. That will be shared. How it will share, that is there are two various methods are proposed. One is group method, another is master slave method, or power balancing using model predictive control methods. So these are some of the methods which decides the power sharing of the different DGs and ACs. So dispatch power control mode already I told. In standalone operation, so power management and control strategy are focused on the microgrid AC voltage and frequency control as well as demand power sharing among DGs and SCs. Various schemes have been proposed to realize this. Broom method is most common. Broom method emulates the behavior of synchronous generator where voltage and frequency vary with the output P and Q of DG. Here the output P and Q of each source is determined in order to regulate the frequency and voltage of AC bus on their desired value. Other than loop control, DGs can work on their MPPT and SCs as storage energy systems, control AC bus voltage and frequency. In other words, SCs balance the demand and the generated power. SC balance the demand and generated power in order to regulate the frequency and voltage of AC bus. There are other power management schemes that can be used in standalone AC couple hybrid microgrid, such as power balancing using a model predictive method or heuristic method. So in case of DC couple microgrid, in DC couple microgrid, as we know, there are two bus, AC bus and the DC bus. So accordingly, we have to go for this AC bus voltage and frequency control and DC bus voltage control. DC bus control. These both should be taken care. So in case of when utility is there, AC bus voltage and frequency when it is connected to grid is maintained by this utility grid. But if it is not there, this AC bus voltage and DC bus voltage frequency of AC bus all should be maintained among these converters. Now see, if it is grid connected, it is connected this, it may be dispatch power mode or it may be undispatched power mode. In dispatch power mode, IFC, this is IFC, these are IFC. IFC DC link voltage control mode. This is for controlling the DC bus voltage. DGs and AC, these DGs and ACs dispatch power control mode. So there will be power control mode. So this is used. In case of dispatch power control mode, one method is that this interfacing converter is mainly for controlling the DC bus voltage, DC link voltage. And this DC, DG and AC, DC and storage elements. So dispatch power control mode. So they are supplying power to the grid. So at constant voltage and constant frequency via controlling this converter. This is an AC dispatch power control mode, that is power balancing. So in case of dispatch power mode, another possibility also there. So now say DC, DG, AC, DG and storage element all are utilized for controlling the DC bus voltage. Okay, DC bus voltage, DC link. And this IFC is power control mode. That is, this can be used for power control. So two options are there. One is that this IFC is used to control the DC bus voltage. At that time, this DG, this AC DG and DC DG are utilized for power control mode and the storage element also for power control mode. In other option, these are utilized for controlling the DC bus voltage constant. this is, and this is used for power control mode. By controlling this, it is used for power control mode. Okay, this is dispatch. So in case of undispatched, all the things are supplied to the grid. We are supplying to this grid. So here IFC is there. IFC DC link voltage. IFC is control DC link voltage. This voltage is control, and this is this DC and AC DC for maximum power point tracking control mode. And SCs are charging on. SCs are charging on. In this case, these are for MPPT control. This is for DC bus link voltage. This is undispatched power control. Now come to this standalone mode. Here we have to control the standalone mode. This is not there. We have to control AC bus voltage and DC bus voltage. So when DC bus voltage control mode is there, then this is a DC bus voltage control mode is there. These DGs, AC DG and DC DGs, DC bus voltage control directly. So it may be loop control method or indirectly a power balancing method, etc. And in case of AC bus voltage, so this IFC, AC bus voltage control method, IFC, AC bus voltage control. IFC is AC bus voltage. We have to control this one also in standalone. So in case of AC couple, AC-DC couple microgrid, here AC-DC couple, it may be grid connected, standalone, grid connected, dispatch mode, and dispatch mode. So it is like this. This ILC, interlinking converter, that is converter between AC bus and DC bus voltage control mode. So ILC is utilized for in case of the dispatch power control mode, DC bus voltage control. And DG and SCs are AC bus voltage control. In this way, so various strategies are listed here. Now, in case of transient transient condition means there is a when microgrid is connected to grid, this is grid connected, and when it is not connected to grid, it is islanded or standalone mode. So when you turn that the grid connected mode off, means it is shifted to standalone mode, and or say from standalone to grid connected mode. This is a we have to connect it. So this is actually there is a transition between grid connected and standalone operation mode, or standalone operation to this. So in this case, some transient produced. So transition between grid connected and AC operation mode should be seamless. It should be seamless and smooth to minimize voltage and frequency disturbance and deviation, and ensure balance power flow to prevent DG overloading and circulating power. Transition from grid connected to standalone. There are mainly two groups of control strategy. Say grid connected to grid connected to grid connected to standalone. Two modes of strategy. One is switch off control strategy from current oblique power control in grid connected to voltage control in islanded mode. So this is one. That is switch off control strategy from current control or power control mode, which is there in the grid connected mode, to voltage control in islanded mode or standalone mode. So this is first one. Or it may be uniform control in the grid connected mode to standalone operation. From grid connected to this, it may be switch off, or it may be uncontrolled, uniform control in both grid connected this. That means in second one, this shifting from grid connected to standalone is uniform. But first one, in grid connected mode, it is current control mode or power sharing, power control mode. Now, when you have to transfer this one to standalone mode, you have to switch off strategy from current control mode to voltage control mode. Okay. So another one, uniform control in both grid connected and this. This is a grid connected operation. In standalone to grid connected mode, control strategy is there. Standalone, we have to connect from standalone to grid connected. Switch of control strategy in standalone mode, it is in voltage control mode. So we have to shift from voltage control mode to current control mode or power control mode. So switch of control strategy from voltage control in islanded mode to current oblique power control in this, and uniform control also this one. Okay? Or other one is standalone to grid connected. We will go for the synchronization. It may be passive synchronization or active synchronization. So this is same thing I always, already explained. So this one. Transition from standalone to grid connected. So now this one is already, it is over. Now say synchronization. Here, other than control strategy, switch off from voltage control to power control or through the uniform control, an important task is that the microgrid voltage should be synchronized with the grid voltage before reconnection. This should be synchronized. There are two types of synchronization. One is called passive synchronization and other is called active synchronization. Passive synchronization, here the microgrid voltage and main grid voltage are monitored, and the two grids are connected when they have the same phase angle. This method is based on the assumption that microgrid and the megrid have a very close voltage magnitude and slightly different frequency, which is typically the case. It is the easiest and probably the most practical method so far. However, this method will lead some transients upon the reconnection of the two grids due to no, due to not exactly matching voltage magnitude, and it does not guarantee a fast and controllable synchronization process. So active synchronization, the microgrid consists of different DGs, severely changing electrical load and energy storage. The synchronization of microgrid is quite different in comparison to the single traditional machine. Here, coordination of multiple DGs and energy storage is required. In active synchronization strategy can be classified into two categories. One is one or more DG initiate the synchronization process, and rest of them and the other DG follow them. First, we have to synchronize one unit and other unit follows them. Secondly, all DG take part in synchronization process. So this one, say one or two DGs are take part in the synchronization process. One is mainly used in the microgrid that some DGs are working on the control mode, working on current control mode, while the other working on voltage control mode. Number two is mainly used in microgrid that all DGs are working on voltage control. After synchronization, microgrid will be reconnected to the grid at the voltage 0 crossing. In both the types of synchronization strategy, communication system is essential in order to communicate the system information among the power sources. So power balance strategy under different loading condition. Here I am keeping this one. I think time will not permit me to explain everything here. Just in one slide I am giving here. The power performance of microgrid depends on the load and the grid condition. Hence, robust current and voltage control is needed in this condition. In the presence of nonlinear unbalanced load, which results in unbalanced voltage and at point of common coupling, various control strategies have been used. In case of constant power load, there are mainly interface by active rectifier to an AC grid or DC-DC converter to a DC grid cause instability problem in the microgrid because of their negative impedance characteristics. These problems have been studied in different researchers using small signal method and large signal method, and various solutions have been proposed to ensure the system stability. Various solutions include oscillation compensation technique used to increase the stability margin, active damping technique to overcome the negative impedance stability problem, nonlinear control of AC/DC controller, etc. So there are communication system in the microgrid also. The control and power management strategy can be classified communication based and communication less, CB and CL. In CB, the system information such as current, voltage, power is communicated to determine the operating point of each DG. In CL, DGs operate independently. Communication-based system may affect the reliability of the microgrid. However, it can further improve the power quality, accuracy, and the protection issue compared to CL method. So communication technology, microgrid can be classified wireless technology and wireline technology. So these are available in different literatures. Recently, in order to serve as the main networking technology, different wireless communication technology such as cognitive radio have been proposed. So implementation example, I shall not discuss this one. I think it will take time. How this control technique is implemented. So I shall provide this slide. You can prepare from the that paper also, that referred paper. Here one paper implementation example of power management control strategy, reference 11. It is clearly given how we can control, apply the control strategy. So this group control method, Shivanjibi,
Ah, sir.
how much time I can deliver?
Sir, you can take, sir, another 15 minutes, sir. No problem. Sir.
Another 15 minutes. Okay,
Yes, sir.
okay. No problem.
Okay, sir.
Acha, through control method, let me finish some portion of this one. That I can finish all this. So, through control method can be applied for both DC and AC bus. In an AC loop control method, AC bus voltage and frequency are controlled and the demand power is shared among the input power sources. In this method, is DG and storage elements on an AC bus accompany with its power converter and ILC are modeled as inverters connected to AC bus through coupling impedances. In this method, is DG and AC, DC DG, on the AC bus accompany with its power converter and ILC are modelless inverter and connected to AC bus through coupling impedance. To emulate this loop control behavior, emulate the behavior of synchronous generator, power and frequency group, Q and V, active power and frequency group, and reactive power and voltage group characteristics are programmed to the converter control. In order to make the sources share the demand power in proportion to their power rating, group coefficients should be adjusted in inverse proportion to their power. Group coefficients should be adjusted in inverse proportion to their rated power. Now see here. There are two DGs. Say DG1, DG2. This DG1, DG2. This P1, P2, P1 star, P2 star, Q1 star, Q2 star. These are actually reference active and reactive power of the DG1, DG2. So P1 star, P2 star, Q1 star, Q2 star. Okay? These are reference active power and reactive power. Okay? So and F star is reference frequency and V star is reference voltage for a particular disease. Now this is in a microgrid, this voltage V should be constant, frequency should be constant in case of AC, DG, AC. Now, this F star should be fixed. P1 star, P2 star, this should be reference. So, power shared by this unit 1, DG1, DG2. And this is reactive power shared by DG1, this is reactive power shared by DG2. Now there is a limit of this P and Q. Say P1 max, P2 max, this is the limit, maximum possible limit, possible output of real and reactive power. According to this figure, these is produce their reference output, active and reactive power at the grid frequency and voltage V dash, V star and V naught by adjusting the group slopes M1 and M2, N1 and N2. So slope of this DG1 is there's a frequency versus P curve is like this, and for DG2 this is like this. For DG1 slope versus slope of V versus Q curve is this one, N1 and N2 are the slopes. So by adjusting these slopes, we can we can regulate. DG produce the reference output active at the grid frequency and voltage F star and V star by adjusting those coefficients. That is by adjusting M1 and M2, N1 and N2, we can control this. So in addition to the aforesaid group method, direct group control method in non-dispatchable DG such as wind power and PV system and inverse group method is used. In this strategy, the input of the group controller blocks are the PCC voltage parameter, amplitude and frequency, and outputs are the reference active and reactive power. In other words, in inverse group, PF and QV group characteristics are used to change the active and reactive power generation according to the control of voltage and frequency. In this strategy, DG works on output power control mode to provide the grid support. So this is for DC, this one DC system. Now come to this future trends. Considering the increasing penetration of DC voltage-based RE sources, energy storage, and DC load, that is DC voltage-based REs, energy storage, and DC loads. So yeah, their penetration is increases, as well as the existing widespread AC system. Hybrid AC DC microgrids are inevitable parts of the future power system. Here some discussion and recommendations about the future trends of hybrid AC DC microgrids are provided. Now the future trends, first one, structure of the hybrid AC DC microgrid. AC coupled hybrid microgrid have the dominant structure up to now because of its simple structure and control strategy, AC coupled microgrid. However, with the increase of modern DC load and the necessity of connecting more renewable sources and energy storage system into the grid, AC DC coupled hybrid microgrid are the future trends of power system. Trends of power system. However, in this system, control strategies and the power management strategies are the major concern and challenge. Future AC-DC coupled microgrid will be several DC and AC buses in different voltage level and maybe frequencies if there is high frequency link. As a result, DC bus voltage control, power management within the DC bus and AC bus and grid load and AC bus voltage and frequency control, if necessary, are the main power management and challenges and objective. Moreover, the operation of ILC connecting different DC and AC buses in different voltage level can be an interesting research topic in future. Now, power quality issue in future hybrid AC-DC microgrid with more interfacing power electronic converters from the DGs and SCs and the loads together, increasing nonlinear load, power quality will be an important topic. Currently, harmonic unbalances voltage shakes we have already caused concern in today's power distribution system, and it may get worse in near future. However, with increasing utilization of DGSC IFC, they can be properly controlled to help address the power quality issue. This is a promising area as most DGs and SCs and interlinking or interfacing converters in the hybrid microgrids are not operating at full rating all the time, especially true when considering intermittent nature of our resources. Therefore, development of ancillary services such as flicker mitigation, unbalanced voltage compensation, harmonic compensation, power factor correction, etc. can be a good research direction in future microgrid system. So parallel operation of ILC and IFC. ILC and IFC are the critical link between AC and DC bus in hybrid microgrid. Their control is the key for the power balance between AC and DC subsystem. ILC and IFC will be typically have parallel converters operating together. Therefore, parallel operation of this converter and their control strategies are an interesting topic for future research. Communication system is also an important research area in future since there may be multiple links between DC and AC buses at various locations. In addition, as discussed earlier, IFC and ILC can be in power control mode, DC voltage control mode, or AC voltage control mode. However, it is not necessary for all parallel IFC or LC to work in the same control mode together. So, for example, an AC-DC coupled microgrid, it is possible that some ILC control the DC link voltage, some ILC control the AC link voltage, and some ILC balance the power. This combination of control strategy requires further study and investigation. However, more performance of parallel IFC during the microgrid transition between a GC and SA operation modes need to be considered in future research. So communication system, this technology will be both wireless and wireline technology. Future microgrid will most likely consist of combination of various combination technology. So this may be a future research topic. So transient power management under different load condition, this may be, although these challenges have been considered separately, different researchers considering the real heavy microgrid, transient power management under different load grid conditions need to be further studied in future research. So these are the references of my presentation. For the,
Any queries, participants?
So any query, any question from the audience?
Hello. Good
Hello.
afternoon, sir.
Ah, yes.
Yes, sir. I have one basic query that many papers and literature I have read, they are using basically PI control for this decoupled current control technique,
Yes,
DQ
yes,
control for grid connector inverter. But
yes,
few papers are also there which talk about other nonlinear techniques like SMC based
yes,
control
yes,
or
yes,
model
yes.
predictive control. So what is the basic difference when we are going from PI control to some other nonlinear technique?
Okay, okay. Acha, there is actually, there are many nonlinear control techniques I have also seen in many papers. Okay. Now, I have discussed this matter with my power electronics based colleagues of our institute. Actually, in the control logic, they always preferred till now they prefer PI control, and PID also not used, and I controller also not used. Only that one is used. But if you use, I think performance will be control strategy. Control will be better than the others. That means performance in case of power sharing, in case of group control, if we use nonlinear control, I think it will be better. It will be better, but till now, they are not preferring. Yeah, last time I have submitted one project in DST with a separate controller in the control circuit of the group control circuits of this, but they are not accepting that one. Why they are always preferring this one, but there is a thing in case of nonlinear control, we have to go for the optimization technique. But in practical situation, this optimization technique, that is setting of the controller parameters, different nonlinear control, these are practically how they will use it is unknown. Now, till now, these settings of this PI controller and PID type controllers, they are actually by some fixed set. They are not optimizing the setting. Okay. I think it will give better result with non-linear control. So some study we can propose. That will be published also. Some non-linear control, many papers are also there, but practically whether when that industry will be taken, we cannot say. Okay.
Okay, sir. Thank you.
Okay.
Any other queries? Sir, I think no queries, sir. No more
Okay.
queries.
Okay.
Thank you, sir. Thank you very much, sir,
Okay.
for
Thank
your
you.
very wonderful lecture.
Okay. Thank you.
Thank you, sir.
Thank you.
Thank you.
So, dear participants, next session will start from 3 p.m. Expert speaker is Professor Arunima Verma, IIT Lucknow. So please join 5 minutes before the starting of this session. Thank you.